us by internet. So good morning, everybody. It's a great pleasure for me to introduce you Dr. Naren Ramakrishna. He is the director of Proton Therapy and Neurologic and Pediatric Radiation Oncology and co-director of the Brain and Spine Tumor Program at Orlando Cancer Institute. Dr. Ramakrishna completed his bachelor degree in biology to start your study in biology, and I read in genetics too. And after that, these two fields he studied at Johns Hopkins University and graduate education in Medical Scientist Training Program and Cornell University Medical College, where he received his MD, Medical Doctor title, and PhD in cell biology and genetics. After an internal medicine internship at Mount Sinai Hospital in New York, wow, it's incredible, all the things that he did. So he completed a residence in radiation oncology at Johns Hopkins Hospital, where he was the chief resident. He also completed a Koch Research Fellowship in gene therapy at the Johns Hopkins Hospital Oncology Center and the Radiobiological Institute, and received an AACR Welcome Oncology Scholar Award. Wow. So, Dr. Naren, thank you so much to be here at National University. And Dr. Naren will talk us about the proton therapy, the radiobiology aspect, the clinical outcomes, and the financial aspects. So, with you, Dr. Naren. Thank you so much.
Thank you so much, Maria Cristina, for that very introduction. And certainly more than I deserve. Really, I want to thank, first of all, Maria Cristina and Luis, the whole faculty here, for inviting me and actually just connecting with me such short notice in this area of mutual interest that I think is very important for considerations everywhere. And I agree.
Yes.
And I must mention wonderful Maria Cristina, Dr. Maria Cristina, basically was the catalyst to make all these connections and helped us to start something which I think could be a wonderful collaboration between our institutions. So today I'm talking about a very important subject. I'm an oncologist, a radiation oncologist, and I specialize in the treatment of pediatric and adult brain tumors. And it's actually a wonderful time, to be an oncologist now, because of the rapid advances in technology and also in our understanding of the biology of cancer. So if I compare where we were when I started my career with where we are now, it's just an enormous difference for physicians and for patients. On the technology side, our radiation treatments have advanced using much better forms of focusing dose, imaging patients, adaptive therapy, and also finding better ways to use charged particles, including proteins. And on the systemic disease side, we went from essentially relying on toxins to developing human therapies, targeted drug therapies. And so I know many of you are in medical physics, but you're supporting a very important endeavor with the science that you do. And that is on this local therapy technology side, creating the the best possible outcomes for patients in an increasingly complicated set of paradigms for treatment. So I want you all to reflect on what is the place of advanced local therapy, such as proton therapy, in the exciting but very expensive cancer therapy armamentarium. And I think it's very important to understand the balance between modalities that is necessary in order for patients to have the best outcomes and how that changes over time. One of the most important consequences of our improvements is that patients are living longer with fewer side effects from treatment. And this means, of course, that our local therapy techniques have to be much better, and we have to avoid acute additive effects of treatment. So I know that Columbia doesn't have, for example, a proton center, but X-ray treatment is a wonderful modality. It's the mainstay of radiation oncology, and it keeps getting better. And I would say that the gap between X-ray treatment and proton treatment has shrunk to some extent, over the last decade. And the benefit of this improvement in targeting dose, adapting dose, and so on, is that we continue to improve the therapeutic ratio, which is the goal of all cancer therapy. So, beyond X-rays, we have charged particles, and this is an area that I think all of you are excited about. We have neutrons, protons, carbon ions, alpha particles. I know that Maria Christina has worked with alpha particles. And, but protons are more or less the particle of the day, if you will. If you don't have them, you typically want them. And when you think about particles, of course, you can be quite philosophical about when a star explodes, or even when it shines, we get our photons. But we also get a shower of cosmic rays, and so do the astronauts, including high-energy protons. But which of these is the better tool? So I think all of you realize that protons have some inherent spatial advantages in comparison to X-rays, even IMRT. And this is something that got us excited at Orlando Health even several decades ago. So just to get a basic understanding of how we use protons clinically, we basically take hydrogen and take off the electron, then we have protons, and then we put those in the center of a supercyclotron and create basically a charge gradients, which allow it to accelerate to around 0.6 times the speed of light before exiting towards the target. And then, no doubt all of you have seen the Bragg peak, and this is our way of characterizing really the inherent dose deposition properties of protons. So what we have is a low entry dose, and then at the depth corresponding to the energy, we have a very sharp release of dose deposition, and then the protons stop, and then there's little or no dose after, with the exception of some generated neutrons and so on. This is in comparison to X-rays, where your entry dose is typically higher, and then you produce your dose maximum very close to the surface, and then you have a tail dose which continues and continues to a great depth. So the problem with protons, even though we understood these properties back in the 1940s and 50s, was that producing them was extremely complicated and expensive. So for about a half century, it really remained the domain of only a few centers. But then a company in Boston called, at the time, Still River, developed a superconducting supercyclotron. And actually, at Orlando Health, we were one of the first partners with that company as they were just starting out. And we're one of the 5 initial orders that were placed for this unit, which turned out to really be a great buy for us. So the program was proposed in 2008, and I was on the faculty at Harvard at that time, and then I decided to move to Orlando as a result of this. 2016. This is the synchrocyclotron being lowered through the roof of the center and the scale model for case. That was XP 2016. So this is kind of what it looks like. At the time, we were one of 60 worldwide, 125 in the nation. And our assets in the department are quite extensive. We have MR-guided LINAC, we have adaptive radiotherapy, ethos, and two-tone therapy units, and so on. So we have a full suite of technology. I know that you're planning out a space for a unit, and we picked this particular unit because of cost, but also because of size, because size really also is a big part of the cost. And these are specifications for the bunker that can be used at a minimum for this. And I can give you much more information about it. We did a comparison because we're adding a second unit now, and we did an updated comparison of all of the single vault systems, and these were the minimum requirements for each of these. So it's quite significant, especially from structural costs. So basically, this is a 3-story building, and the patient is on the second floor for treatment, and then the gantry swings around the third or the second and basement floor. And we have a robotic couch and image guidance in the room using a CT. This is a cross section, and you can see the gantry mounted synchrocyclotron. It's amazing that it's that small, but they've managed to do. And this is our CT image guidance system, and we use it for actually quite a lot of our cases. We were the first single room proton center to incorporate CT image guidance. And this is our patient mix, and this is very important for you to think about, because one of the most important decisions you'll need to make for Columbia is really what should the patient mix be, and then what is the overall economic impact of this in the context of your broader health system. Our site, unlike some in the US, where they're really rely completely on prostates, I mean, we started off with 30% prostate, but we ended up now with essentially a distribution between peds, breast, CNS, prostate, head and neck, thorax, and even some pulse. So this is a slide that shows how protons can potentially improve radiation outcomes. And one way is by increased dose to the tumor and with dose escalation resulting in tumor control. This tends not to be as dramatic as it was 20 years ago, because X-ray systems have gotten quite good for dose escalation as well. But we sometimes still can get a little bit more dose with protons than with photons. Where we really find the benefits are in a subtraction of acute, early delay, late effects, and then reduction in secondary cancer. And the critical parameter that affects how many of these benefits are actually observed in the patient is the life expectancy. So you'll remember that the second slide I talked about, or third slide, how patients are now living much longer. And so the potential benefits from radiation treatment are also potentially much greater for proton therapy, potentially much greater for these sort of things. So here are some examples of what proton therapy does than conventional radiation. Shall I go?
Let's try to
I'll Sorry about that. So what is the reduction of integral bits? This is an example of the two-field electron. This is an iron. This field looks very similar also. Don't include some of these activities, but this reduction in the volume of tissue getting the high nucleus in the setting of this, which is prostate, can reduce the risk of secondary malignancy, and so an economic argument could be made for that reduction. A study then by MGH looked at the risk reduction based on theoretical models and outcomes that had been seen long-term for X-ray treatment. And they predicted that the risk from photons for a secondary malignancy would be as much as 1/4 that of radiation with X-rays. The classic application for proton therapy, of course, is craniospinal radiation. And with craniospinal radiation done traditional methods, we end up with a very large dose wash throughout the thorax. But when done using proton treatment, we're able to certainly reduce or eliminate dose to the anterior structures. Moving to adults, one of the applications of proton therapy that's quite exciting is in the reduction of dose to the coronary arteries, which is thought to be a major cause of potential long-term morbidity for breast cancer patients, particularly with left breast cancers. This is the excess dose that would typically be delivered to the heart and to the rib cage as a result of photon treatment rather than proton treatment. And we see that patients with left-sided breast cancer have an increased incidence of myocardial infarction in comparison to those with right-sided cancer when both of them are treated with X-rays. So there's a theoretical argument there that we can achieve a major improvement in terms of long-term health outcomes using proton therapy. And in fact, multiple clinical trials are underway that are examining that question. There are other tumors in the thorax which may also benefit from proton therapy. One is Hodgkin's. This is an example of the difference in dose using conventional IMRT or proton treatment. And you can see that there are quite significant reductions in heart and lung dose in many patients. Lung cancer is another area that we treat quite a bit. And in this setting, you can see that the difference or the excess dose given by IMRT could have quite significant functional implications. And in fact, MD Anderson reported a study looking at toxicity for esophagitis and pneumonitis and saw dramatic reduction using protons versus IMRT and conventional, even using a higher target dose. Of course, my clinical area of specialization is the brain, and the argument for protons in the brain is quite strong. We can often dose escalate with protons, especially for tumors that require high doses, like chordoma, chondrosarcoma, atypical malignant angiomas. We're less sure if glioblastoma benefits from higher rates. There's a clinical trial that's examined that. And we also, of course, can be less dose of surrounding brain, which is especially critical for the lower grade tumors and benign entities like ADM. So, in the brain, the stakes are very high. We've seen that as little as 1 to 3 fractions of whole brain treatment results in acute declines in verbal memory. And we understand that dose to the temporal lobe is a critical determinant of this. And from preclinical neurine data, which was actually done by one of my colleagues when I was at the Dana-Farber, showed that you actually were depleting stem cells, or could deplete stem cells, which with as little as 10 gray or less. And when we look at the cognitive domains that are compromised by radiation, especially for pediatric patients, they include all of the major areas. So essentially, the entire brain, its connections and network are all affected. We've learned that the hippocampus is a very crucial part of radiation sensitivity in the brain. And this is an example of a patient I treated, a 32-year-old, who ended up having a brainstem tumor. He ended up undergoing a biopsy, had an H3K27 mutation, which identified him as a diffuse midline glioma. And so he was one of our early patients with protons. We created a contour for treatment, and then we compared IMRT proton. And then when you subtract dose between the two plants, you can see that the excess IMRT dose would have gone to areas, including hippocampus. Not only are there effects on stem cell populations in the brain, but we also know that excess radiation dose also has effects on mature neurons. And so our theoretical understanding now is that any dose of that dose in the brain and using proton therapy allows us to reduce even those low dose areas. And this was a study that was done by Ramakrishna and colleagues at Mayo Clinic, and basically showed that using proton therapy, there was a significant, which is this right here on the top, there was a significant difference in comparison to using whole brain radiation techniques by using X-rays in terms of IQ declines in up to 10 years post-treatment. So, I've talked a lot about the benefits of protons, but I hope you don't mind if I also talk about the potential drawbacks of protons, because they're definitely, I mean, the advertisements, it's important to understand what we have. So, the benefits we've already talked about, but are any toxicities increased after proton beam treatment? I think it's an important question. So ACNS 0121 is a children's oncology group study of pediatric pneumoma. And it preceded the current one, which is 0831. And what people were noticing, and it was just kind of a chatter, was that with photon treatment, brainstem necrosis was really rare, less than 1 in 100. But then on protons, in a small population, they saw 1/10 of the patients getting brainstem necrosis. Here's a patient that actually came to me from California after getting treatment following this protocol, which was written for both protons and photons, and received craniospinal radiation with a boost to 59.4. And this was for a mentalblastoma. Completed in April of 2016. This was done at Scripps Clinic, which is a very well-known hospital in San Diego. He developed progressive brainstem necrosis starting in November 2016. Now, this brought up a lot of questions. And so all of the major centers pooled their data, and and all of these were, of course, proton centers. And basically, what I would say that what they found is that brainstem necrosis does occur with protons. It probably occurs at a somewhat higher rate, although there was quite a bit of controversy with that. And some of them denied that it occurred, but all of them lowered their dose tolerances for the brainstem quite significantly, which tells you a lot. So I've been doing this for 20 years. For the first 15 years, I never saw brainstem plasticity in any patient I treated. With protons, it happens. And this brings up something that's really important. This is why it's so interesting to study protons, right? And that is that we don't know a lot about the biological effects. We have an approximation of it, but we don't know. And these are the consequences when we don't know. So now we'll get to a little bit more of a critical section. That is, we've done proton therapy for half a century. Is it as good as it could or should be? What are the obstacles to realize its clinical potential? And what progress have we made in addressing the fundamental issues which affect outcomes? So, one of the most important things is, all of us are familiar with the BRAC peak, but we don't treat people with a BRAC peak. We treat people with spread out BRAC peak. no tumor is going to be just sized just right to be treated by that little peak there. Right? So what happens is you add together basically different valence of their own energies. You form spread out rag peak like this, right? But at the same time, your skin dose changes dramatically. It's no longer this really nice skin dose that you were getting, a single peak. Because your rag peaks are staggered, but your skin dose is the same as adding. So when we treat breast cancer patients, for example, with protons, the skin reaction is just horrible. And then the question becomes, do you design your proximal dosing to account for that? These are the controversies that we cover. So until, I would say, 2010, the majority of proton systems being sold were passive scattering systems. And that's what we got, because that's what was available at the time. And basically in a passive scattering system, you have a range modulation gate, spreading your beam longitudinally, and then you create custom brass apertures and compensators for each patient. And you get excellent distal shaping, really nothing wrong with that. Your proximal shaping, though, is very, you have very little control for range. You do generate some neutrons from the material in the beam path, but these systems do have the advantage of delivering the dose all at once, and not having scaling issues and so on. IMPT, now essentially every system that gets sold is IMPT. And IMPT does away with the range modulator as well as the compensator and so on. Everything is done using scattering mechanics. And this allows certainly improvement. It's not a quantum improvement by any means, but there is a small improvement in comparison to proton scatter, passive scatter for some patients, but not all patients. So the ideal setup, honestly, is to have both. That's what we're going to have when we get our signal. But both have their pros and cons. But here are the things about protons that aren't in the advertisements. Unlike photons are incredibly sensitive to changes in material and in heterogeneity. And what ends up happening is, because of this range uncertainty, we treat bigger targets. We create bigger planning volumes for photons. It's something that you don't think about until you actually start doing the treatment. Now, the larger something gets, the less these absolute effects tend to be. But for small targets, it can be quite significant. The other things that affect protons a lot are change in motion. Because when you change motion, then the path of the proton can be traversing a very different density. And so there's a much greater effect on proton planning than IMPT, and arguably a greater effect sometimes for IMPT than passive scattering. So we're trying different tricks to try to understand the dose that we're delivering better. One is using essentially secondary emissions that are that are generated by proton treatment, just like basically the patient turns. It goes into a PET machine, after the proton treatment, and the gamma camera can pick up these dose emissions, and then you can actually see biologically what dose was truly delivered. These are things that are still in progress, but they're not yet of the quality to use in the clinic. So, but the implications are big. If you have the wrong range for your proton beam because of setup errors or changes in body composition, this can negate the benefits that you were trying to achieve. So we get then to the question of linear energy transfer and relative biological effect of protons and why it matters. Well, so you're going to be studying linear energy transfer, relative biological effect, and it's going to be critical for you to understand the impact of linear energy transfer on relative biological effects. So, for the last half century, we've modeled relative biological effect by this approximation, 1.1, which relates cobalt gray equivalent to gray. Does anyone think that this is accurate? Well, it's useful. but it wasn't active for this young man, right? So the question is, how do we predict when this ratio serves us and when it doesn't? And what tools are you going to use in order to avoid these sorts of terrible things happening in our patients? So, right now, the planning systems that are available have either no or somewhat rudimentary tools for assessing biological dose. Dose that's based on linear energy transfer and a transformation of that into relative biological effect. There are attempts being made to do this, but physicists like Dr. Ramakrishna are using tools that are actually quite difficult. Monte Carlo modeling tools like GN4 and Topos Bio. And we use them too, but it's not feasible to do that on a clinical basis. Those aren't clinical tools at any rate. So this is a very critical time. Now, this RV certainty is important, not just in our clinic patients, but really in every area where we're looking at the impact of charged particles on basically disease. It could be in large populations, it can be in space dosimetry and so on. And so this is a question of great interest. When an astronaut is in space, how do we calculate the true biological dose that he's receiving? So these are some examples. This is out of MGH, of linear energy transfer base dose plan. And it shows you that there can be wide differences between what is predicted using a linear energy transfer-based plan or a conventional dose-based plan. This is an example of using LET-based planning for a case just like the one that I showed you, which had the catastrophic brainstem necrosis. And there were really quite dramatic differences seen in the predicted dose, or true dose, if you will, using the two systems. So these are going to be critical questions that you're going to be addressing as we move forward. Now, an area of research interest for me is trying to understand in each patient what is the effect of these charged particles and how can we follow it and perhaps make predictive metrics using available radiographs. This is actually work that was done by Ramakrishna and colleagues at MD Anderson at the time, and they looked at ependymoma patients, and they looked at what was happening in the white matter after a certain proton dose or a certain photon dose. And what you can see are differences in radiographic signal that emerges, differences in the timing of the signal, differences in the quantity. And this is a reality of modern clinical radiation oncology with protons, is that what happens on the MRI is very different. And so we'll talk about this for research purposes, but this is one of the areas that my team is working on in terms of aggregating photon-proton cohorts and then comparing radiographic outcomes to develop predictive metrics. So in this particular study, what they looked at, white matter changes as a surrogate for radiation biological effect, and what they found on their univariate analysis was that proton treatment was the significant factor which would, versus minority, which would predict for this effect. Okay, and now I want to come to an area that Maria Christina wanted me to speak about. And that was
Okay.
and that is proton therapy cost effective. And so I just wanted to briefly touch on that. Proton therapy is extremely expensive. Proton system installation now costs between 30 and 50 million US. And it's been difficult to do really accurate cost-benefit estimates because there's a lack of long-term clinical data for protons. And it's important to know also in the US, proton centers are not all done well. About 30% of them actually went into financial insolvency. And so, as an economic sort of argument in sort of a free market like the US, protons have been a difficult thing to make work, and probably because there's too many of them to use, quite frankly. So, some of the key features for viable proton centers are utilization. And that just means that you have enough patients with a large referral base. And then you also have to keep it up because the machine issues with proton systems are quite a bit more significant than photon-based systems. So, again, the tools that we use are incremental cost-effectiveness ratio. I've done research on this, and we'll talk to your research team on later. And the methods that we use to assess cost-effectiveness include modeling studies. Typically, we use Markov cycles. We can also use Monte Carlo methods. And then we generate, basically, an incremental cost-effectiveness ratio and look at the costs associated with any quality-adjusted life years that are gained. So we can classify broadly the data to show that there's a definite benefit for pediatric brain tumors. It's indisputable. There's a likely benefit for other pediatric sites, selected left-sided breast, selected locally advanced non-small cell lung cancer, and high-risk head and neck cancers that you couldn't treat to a high enough dose in any other way. There's not likely benefit for prostate early stage non-small cell. These have all been examined. So this was actually sort of a major study that looked at proton therapy for the prostate. And there's a lot of criticism in the US about proton therapy for the prostate, but men believe it to be better, and so they seek it, and some of them take cash. So this is a typical Markov state analysis, and the typical sensitivity analysis parameters that we use. So, just briefly, in the context of Columbia, because we talked about this, when we wanted to think about cost effectiveness here, in comparison to the other economic studies that you might find in the literature, you're basically only going to be making a few changes in your sensitivity analysis: treatment costs, toxicity costs, quality value, and you're also going to put a special emphasis, since this is a future-based plan, on the effect of patient mix and effect of longer overall survival for mixed modality patients, because that will change sort of the actuarial late effect quality or utility costs, as we call them. You'll also want to add into the model the indirect impact, which is halo effect, research, reputation, and potentially the benefits of medical tourism for an entire facility. So these are things that we'll talk about. So I want to briefly touch on the assets that I have for collaboration. So I've collected proton therapy outcomes since 2016. We are in the process of image aggregation of essentially all MRI studies for all the brain tumor lesions. I've signed a research collaboration with Visioneer. Visioneer is the first artificial intelligence-based auto-segmentation FDA-approved company, which is it's a landmark for brain tumors, and it's going to allow us to automatically segment this vast library of images, and once they're segmented, we can subject them to radiomic analysis and everything else. So it's going to be quite exciting. I've also set up a research collaboration with a company called Photon, which is very exciting. I don't know if many of you are familiar with the Human Connectome project, but that's really I say the space mission of our time, in a sense, exploring the human brain. It's the first map of the human brain that's been made, and using that map and then all the variations that were found, different maps related to functional brain imaging, artificial intelligence has been used to rapidly generate functional brain pathways for patients just on the basis of diffusion index and MRIs. It's really quite exciting. So we've also set up a radiomics and image analysis pipeline. The research team at our institute is 12 medical physicists plus 4 residents. And my personal research team is 20 medical students. Here they are. In Orlando, they're from University of Central Florida and Florida State University. Very bright students, and they're quite excited about our collaboration. I asked many work from Columbia, not work, but many speak Spanish, so that will also be a very helpful asset for us. So that's basically my talk. Thanks so much. Any questions?
Any questions? I will try to translate this. Thank you. Did you know that technology change or change the area? For example, electronic supercomputer. Yes.
Yeah.
The question is because the heavy gantry is 600 tons. Yes. And this new technology, the cathode gantry tolerated heavy 10 tons of mass. Yes. Do you know this new technology?
It's not commercially available. That's the problem. Yeah, sorry. I think, well, yes, there's a number of different proton systems using different fundamental technology that are not yet FDA approved, but there's certainly interest, and those could lower costs of proton therapy quite significantly in the years ahead. No question. It's quite exciting work, but not yet clinically ready. Probably it might be possible to partner with a company like that and do some sort of research work, but it's not yet commercially viable.
Hi, Dr. Naren. Thank you for your presentation, for your talk. And can you recommend us some institutions for the financial support in the way of these type of projects for Colombia?
Yeah, that's a very important consideration. And it's very interesting that the company that Orlando helped work with in order to make this project viable, they actually have relationships, for example, in Ecuador, not for protons, but for gamma. So there are companies like them, which basically will absorb the cost of machinery and then share the and you will probably build the center, and then they will work with you to split the income. That can be viable, because the capital costs are quite big.
Firstly, Dr. Naren, personally, this is an honor to me, and first of all, to hear this presentation. It's really impressive, and from me and medical physics research program, thank you to accept this invitation. Even though I was wondering about which is what is the cost of the life of what is the cost of the lives of the patient? For example, if we have some couple of patients with terminal cancer, and if we treat with this kind of treatment, and in terms of time, which is the cost of the life of, which is the time that this patient is going to be extended.
Well, that's a critical question, and that's really what we try to understand with the cost effectiveness research. The problem is it's difficult to predict for an individual patient what the actual benefit will be. So we can create probabilistic statements regarding what is the probability distribution of expected outcomes for these patients and compare that between two treatment types. It's an important one, and the difficulty with proton therapy and estimating this is, there's a number. One is there have been very few randomized controlled trials to give us long-term and unbiased data. Second is, the second one is that basically we have very little also understanding of what is the overall picture going to be in terms of even something as simple as survival in the setting of the rapidly changing systemic therapies, because the survivals are changing, quite dramatically. So it's very important to do a sensitivity analysis for your statistical output.
What is your concept about between proton therapy and carbon ion therapy, please?
Well, if I could have carbon, I'd love to have carbon. But there's only a handful of carbon centers in the world. They're incredibly expensive, 250 million is the going price. And running them is incredibly expensive. They need so much power. One is being built in Florida at Mayo Clinic in Jacksonville. It will be open in about 3 years. Whatever I said about protons is 10 times more true for carbon ions. Our understanding of the biological dose of a heavier charged particle is almost nothing. So we could probably see greater effects, we could see greater toxicities. So the work you're doing in modeling is incredibly important for that. But I think that it has the potential for greater effects because it is almost entirely dependent on direct DNA damage. There's no oxygen enhancement effect, for example, right? Whereas proton still does utilize a significant proportion of indirect ionization for DNA damage. Carbon is essentially none. So high LED radiation, so high linear energy transfer radiation has its own set of physical and biological problems and advantages.
Hi, Dr. Naren. Sorry. Thank you for your wonderful presentation. I have actually 2 questions for you. First of all, you were mentioning about the fact that we're seeing much improved survival in cancer patients. I would like to know your experience with proton therapy for re-irradiation, because I think that that's a challenge we are seeing more in clinical practice as radiation oncologists. So that's the first question. And then the other one is, why do you think that over 50 years of using proton therapy, we haven't found that striking difference with photon that's gonna, make everyone want to have protons and invest the money in it, because it is expensive. I think it's clear that we have a benefit, but why we haven't seen that difference yet?
Well, those are great questions. And I would start, let me work my way backwards. And you're saying, why do we not see this big benefit, or why do we not have more universal adoption of proton therapy? Really the simple answer is cost. It is such a huge capital expense for a hospital to invest in a proton system. And even though it's come down in recent years, it is still extremely difficult to justify unless you have a patient population that's enriched for precisely the patients we know it helps. And those are the ones that I mentioned. Yeah. I think that's the problem. And it's actually in the US, many regulatory agencies are very upset about the increasing cost of healthcare. And proton therapy is a big target because when you can, some of these installations are like 100 million. So they're like, why are you spending that money? Because then you have to recoup all that money in order to pay back your investment. And so I think protons has to be used for the right patients and the right reasons. And the first question was, I'm sorry. Re-irradiation, yes. Yeah. So re-irradiation is a glorious example of what protons is good for. I had another section that I left out because I'm very interested in utilizing what's called spatial fractionation. Mini beams, microbeams of radiation. So I'm interested in proton treatment for re-irradiation because of its spatial advantages. So we use it probably 20% of our cases for re-irradiations. But then I'm also interested in the ability to charge particles to give us more beneficial spatial fractionation. In other words, creating beams that go through tissue without, with a completely different biology than if you used a homogeneous beam. So we've done our GM4 modeling of that process. This is one of the areas that I'm really hoping to collaborate with your team here on. I think it's a fascinating area for re-irradiation.
We have also a question from but I think we have to. Eso era. Se silenció a todos. Hilary, si nos oyes, ¿puedes hacer la pregunta?
Sí, sí, les oigo. Good morning, doctor, and good morning to all. Can you hear me?
Yes.
Okay, thank you. Doctor, thank you for this presentation. The sound is here with a little echo, so I try to understand you. So my name is Hilary. I am studying biochemistry. And my question is, if could this proton beam technique have implications for the structure of DNA at the molecular level?
For the student of DNA at the molecular level, absolutely. I think that, in fact, even here, Dr. Christina is working on modeling of interaction of charged particles with DNA. So anyone that's interested in studying DNA damage repair mechanisms, the use of charged particles is going to provide a very interesting opportunity. When I last had a laboratory when I was in the faculty at Dana-Farber, where I worked also with boron neutron capture and also alpha particles, and looked at the difference in biology at the DNA level between those and using X-rays. So it's quite interesting, a very different cellular response to those types of radiation. So the answer is absolutely yes.
Okay, thank you.
So my question is around the cost benefit definition. There is a thin line enabled to pharmaceutical production in your facility or your non-medium facilities. For thin line for pharmaceutical, for example, FDG.
Right. It's a great question. I'm not aware of any center that set that up as a joint program, but theoretically it could be. So that's a great point. Something interesting to look into.
first is, do you have or do you use flash therapy in your institution? If the answer is yes, what is your experience? What do you think about the radiobiology in the flash therapy?
Well, I'm really happy you asked this question because I think any discussion on photons today is probably complete without flash. Our machine doesn't have an adequate substrate for flash therapy. So we are, of course, following very carefully, and that's why I chose to do mini beam treatment rather than flash, because that also is a different biology. And it's feasible, at other districts. But yes, this really points back to just what we were talking about regarding retreatment, using mini beams, and so on. There is a different biology when you use extreme dose rates. And one of the things to remember is, with flash therapy, they're not using the Bragg peak. They're typically utilizing the portion of the entry before the Bragg peak. So the linear energy transfer characteristics are different there as well. So biologically modeling that is quite important. We've seen anecdotal reports early on of some interesting outcomes. The clinical trials are underway, so it's important for us to see how they turn out. We hope to have the first clinical trial of mini beam therapy. So that will be another way of looking at the difference of biology.
I would like to ask you about the genomic studies for the patient. Do you use the genomic studies to choose the treatment for each patient or personal patient?
Thank you so much, Maria Christina, because this is, of course, what I'm most passionate about is molecular medicine. And so the last 4 to 5 years, because of next generation sequencing, which is the ability to rapidly sequence the entire genome, we've seen an explosion of information for every patient. Every cancer patient gets next generation sequencing. So we have this vast amount of information about their tumor, and we have very rudimentary ways so far of applying it. I have a startup company which is focused on taking all of the next generation sequencing, methylomic data, expression data, biomarker data, and then turning that into a form that you can interact with and visualize. So I think that this is also going to have dramatic personalized therapy implications for radiation oncology. So at this point, very few people frankly understand what to do, except for the most important mutations. But we are generating this huge set of data and applying big data techniques to relate mutations of unknown significance and other non-coding mutations with what we see in the clinic. So very exciting.
Just to clarify, this is the same as GARD, GARD, for radiation genomic adaptive radiation.
Exactly.
Okay.
Exactly. There's a lot of names we have.
Okay.
Maybe in the chat. No. Any more questions here? Just raise your hand. No hands. Okay. Okay, I would like to.
Okay, it's an example. For example, if we have central nervous system cancers, if the radiation oncologist prescribe 54 grams, is the same dose
that we have to use in proton therapy, or exist different dose, prescription? I don't know.
Yeah, that gets back to what we were talking about with the RV. You know, that right now we use a 1.1 conversion factor for dose equivalence, but we know it's wrong in some places of the brain and in some patients, and maybe genomics will play a role in understanding that as well. But there is a difference. It's just that we don't yet understand how to predict it. So for the most part, what clinicians are doing now is they use a different set of tolerances for normal structures between protons, in the brain, between protons and photons, just based on empiric data.
Okay, the last question.
Good morning. Thank you for being here. My question is about you said it's not a good thing to do it with proton therapy. It's not is cost efficient. And I want to know if will be a mixed technique with conventional radiotherapy and proton therapy, or just do about that kind of treatment with protons.
If I understand you correctly, you're wondering if there are intermediate combinations of treatment that where instead of just doing either protons or photons, you might combine the two. In fact, we do that sometimes, but I think it's very difficult, and I actually do it intentionally in the central nervous system. I create combinations of protons and photons in order for me to avoid what I consider is the steep part of the toxicity curve for protons, especially near the brainstem. So I'll often use 15 to 20% photons so that I avoid the exponential rise that you'll see in toxicity when you reach the inflection point, because there's so much uncertainty, right? But we don't yet have cost effectiveness data because of this sort of combination. We don't have enough data to do an accurate biological model of the combination.
There's a question about if you have a way to estimate how the biological models change for protons. If the linear quadratic models changes, I guess the alpha beta values changes. How would you adjust this?
Yeah, no. The linear quadratic model is certainly our friend for photons, but for charged particles and by and large, even to some extent for protons, we have to be very cautious with it and understand that it's even more limited for protons than for photons.
That was the last.
Only a question. In Colombia, we have an person who said that of service cancer. Do you have some experience with proton beams to treat this service?
I would say that gynecologic cancer is one of the areas where protons have not made a big impact. The reason for that is brachytherapy is also extremely good. And, so when your dose is localized so well with brachytherapy, it's very difficult to improve on that with protons. Very few scenarios where protons give you some, even a dramatic dose improvement. So I would say less.
Just wanted to say thank you. Ready?
Close.
And everybody is welcome for the next seminar that will be todo el mundo facilitado en los próximos seminarios que tengamos en física médica. Vamos a intentar hacerlos también híbridos como este. Y bueno, yo creo que nos queda mucho por finalizar. Thank you.